Hello friends, welcome to Machine Tool Design. So today we will be studying the process of hydrodynamic journal bearing design. But before we actually study the design procedure, let's take a quick recap of the process of hydrodynamic journal working and the Hersey diagram. So as we have studied before friends, the Hersey diagram gives a plot of the coefficient of friction versus the lambda parameter. This diagram helps us to basically locate which regime of lubrication is happening in which zone. So if the Hersey diagram points before 1, then that lubrication is boundary lubrication, in which there is almost no liquid, only liquid is present in the molecular form, and therefore there is no separation between the two surfaces. From 1 to point 2 is the zone of semi-liquid friction, in which there is small amount of lubricant present inside the two surfaces, but at the same time it is not enough to completely separate the surfaces, and therefore the asperities of both the surfaces do meet, and therefore we see that the frictional coefficient here is quite large, but as the amount of liquid increases, the friction drops very steeply. Then at point 2 we see that there is complete liquid friction. What is meant by that? That means the liquid is present between the two surfaces, and the thickness of the liquid is such that there is no asperity contact between the two surfaces. So the whatever friction is there, it is because of the internal friction of the fluid, which is very less, and therefore we see that the frictional coefficient in liquid friction is very less. Moving from 2 to 3, we find that this is the complete liquid friction zone. However, at point 3, the frictional coefficient is larger because the effect of turbulence takes place. If you see carefully, lambda parameter also depends upon this parameter omega, which is nothing but the rotational speed. If the rotational speed is high, then there is a lot of churning of the lubricant, and if there is a lot of churning of lubricant, because of that creates a lot of viscous drag, because the liquid is no longer flowing in a laminar flow. Okay, so this was a brief recap of the Hersey diagram. Now let us see how the hydrodynamic journal bearing works in these different regimes. So friends, this is a recap of the functioning of a hydrodynamic journal bearing right from the position of rest to the position of stable operation. Okay, so I will explain the construction. In the construction, one can see that the journal has the small diameter and it is represented by small d, and the sleeve has a slightly larger diameter and it is expressed as capital D. Because the journal diameter is much smaller than the diameter of your sleeve, therefore the journal very easily slips inside the sleeve. Please note that this journal is a long shaft and the sleeve has a finite distance L. So when we talk about the L by D ratio, the L is the length of the sleeve and the small d is the diameter of the journal. Now let us review the operation of journal right from its stalled condition, that is the condition in which it is not moving, to the steady state. In the initial condition, when it is in the stopped condition, because of the effect of gravity, the journal basically sits on the sleeve as shown in the diagram A. The space between the sleeve and the journal is filled with oil, but because of the effect of the weight of the journal, the oil gets displaced to the upper portion of this gap. Now as seen here, the journal is switched on, and when the journal starts rotating in the anti-clockwise direction, the first thing it will do is it will try to climb inside the sleeve. This happens mainly because that there is a proper solid-solid contact between the journal and between the sleeve. So because of this, the direction of rotation which is anti-clockwise for the journal therefore climbs up in the given direction. As it starts climbing, what happens is there is a slight circulation of oil because of the churning effect produced by the rotating journal. And because of the circulation, some amount of oil seeps inside this gap. And as soon as this seeps inside this gap, what happens is the regime of semi-liquid friction takes over. And we know from the Hersey diagram that when there is semi-liquid condition, the frictional coefficient drops very sharply. And because it drops very sharply, we see that this journal slides back because of the reduced coefficient of friction, and because of the inertia, it actually goes back in the opposite direction. All the while it is rotating, and when it is rotating, what happens is more and more oil gets inside this gap. And as we see the thickness of the oil increases, we find that in the final stage there is a complete separation between the journal and the sleeve. At this point, the thickness of the film is H minimum because this is the location where the film thickness is the least, and H maximum is in this position where the film thickness is maximum. In this condition, there is complete separation of the two, and hence this is the condition of least coefficient of friction. Now that we have seen the function of the journal bearing from stopped condition to the stable state condition, now let us go ahead and review the important parameters that should be considered while designing and selecting a proper hydrodynamic journal bearing.